Welcome back. Now we have a look at the next concept, which is the concept of momentum. There's a lot of erroneous ideas about momentum out there in the literature. Sometimes it's talked about as the stopping power of an object, how hard it is to stop an object. That often gives us a problem when it comes to looking at momentum. Momentum has no physical definition. It is simply a mathematical definition. So momentum is, just give me 5 seconds, just get them up there. So there's momentum. And it's got a symbol, which I'll go in a few moments. And it is simply defined as the product of an object's mass and its velocity. So P is the symbol that we have for momentum. So it's actually the letter rho, but this looks like a P, it's just a Greek letter, and it equals simply mv, and there it is, the formula. Now, notice that there is a vector arrow above this, so rho equals mv. This means that momentum is a vector, it has direction, and we're going to be looking at it having a positive or a negative value depending upon whether or not the velocity is in the positive direction or a negative direction. If we have a look at its units, the units of momentum would be the units of mass, which is kilograms, multiplied by the units of velocity, which is meters per second. So it's the kilogram meter per second. Okay, kilogram meter per second. Now, that's the first of our units. We also know that the Newton is the kilogram meter per second squared. So we can also make this, by combining and using the Newton, that the actual other form it could be is the Newton second. It seems to be a funny saying when you first say it for the first time, but the most common units for momentum is the Newton second, NS. Okay. This only works, of course, if the mass is measured in kilograms and our velocity is measured in meters per second. So let's do a momentum calculation. We're going to calculate the momentum of a car that is travelling at a certain velocity. So momentum would equal mass times velocity, and therefore the mass is 1230 times the velocity, which is 16.7. Using our calculator, putting that value in, we get that it's 1230 times 16.7, and that's 21.5, that one there, kilogram meters per second, or, and that's a lot of things you have to write there, or the most common, the Newton second. Okay? But yeah, so moving on. Momentum is one of the conservation quantities. We know that there is a conservation of energy in the universe, that energy is never destroyed, it's only ever transferred or transformed. Momentum is very similar. So momentum is conserved. So the momentum before an interaction must be equal to the momentum after an interaction. The interaction we normally talk about is called a collision. So when an object goes and meets another object, this is an interaction, momentum is transferred from one object to another. So that's how it is conserved. So the momentum before must equal the momentum after, and unlike energy, it is only transferred. You cannot transform momentum. Momentum does not become something else. It is transferred from one object into another as we have a collision or an interaction between the two objects when they come into contact. So that's the law of conservation momentum. It is an inviolable law. It can't be violated. Okay, moving on. Now, Today in the style lesson that is associated with this, you will be using this collision card. So if I get you to go to the style lesson now that is associated with it, and on the style lesson, you will find, there's the style lesson we need to have. You'll find momentum and collisions part 1. So in the first period today, you'll be doing part 1, and in the next period, you'll be doing part 2. When you click the link, you will get this simulation here. Now, this simulation is a crash cart, and I forgot how to explain that. It's over there. Good. Okay. You can change the mass of the red and the blue carts. So to make an increased mass, we just simply do that. It's now 2 kilograms, and the red cart is now 3 kilograms. You can move the cart's motion, initial velocities, by increasing or decreasing it. Okay. If it's a negative velocity, it will move to the left, and if it's a positive velocity, you'll move to the right. So let's make that one move to the right. So the red's going to go to the right there, and the blue will go back, and let's just make it, well, let's leave it as it is. Underneath this stop sharing and hide thing, we've got 3 different types of collisions. We have elastic, which means they bounce off each other. Inelastic, they glue together, and explosion is where you have them initially together and then they explode apart. For the first part, we need inelastic collision. So we're going to select that. And then all you need to do is just press the start button and have a look at what goes on. Okay. So that's a inelastic collision. In the second period, you can have some fun with an elastic collision. So I'll leave everything exactly the same. I might make that a little bit faster, have some more fun with it, and then press the start, come together, bounce off, and out they go. Okay, I might just reset that, restart, and just press play. Where's my play? Start that. Okay, here we are. So before you actually do anything, can you have a fiddle around with how this little app works to make sure that you know how to change the velocities and the masses. You've only got 3 different masses: 1 kilogram, 2 kilogram, and 3 kilogram. This is the explosive collision where they start together and they both start stopped, and then we can get them to explode apart, and bang, there they go. Okay, right, now you've got that, you can go back to the style lesson. Yep. And you are initially going to use the following parameters. You want to select, oops, wrong one. You have to select the following. You want both the red and the blue carts to be initially 1 kilogram. We want the velocity of the blue cart to be 0, so it's stationary before things. And please move it from its position over here into the center. Otherwise, it will just bounce into the edge and you haven't got any readings. And set the velocity of the red cart at its fastest velocity. And we want it to move to the right, so make it 8. And then you'll change that. So you're going to run the simulation and record everything in the table below. So here is the table that I need you to record it into. Okay, let's get it up there. I've done the first line for you. So I've done line A in preparation for you. So it's a large table. I apologise for it. I couldn't find another way, a better way of setting it out for you. So here we are. We're setting the mass of the red cart and the mass of the blue cart to all be 1 kilogram. And the initial run, we're going to set the velocity of the red cart at 8 meters per second. So to find the momentum of a red cart, remember momentum is equal to mass times velocity. and the mass of the cart is 1 times the velocity, 8, and that gives us 8 Newton seconds here. Similarly, the mass of the blue cart is 1, but the velocity of the blue cart to start with is 0. So 1 times 0, remember, once again, momentum is mass times velocity. Then 1 times 0 is 0. So a stationary object's momentum is automatically set as 0, very similar to kinetic energy. Now, what is the total momentum of the system? This is the sigma momentum of the initial system. It's a sigma symbol, that's the momentum, and that's I for initial. Well, initial momentum is 8 for the blue, and the initial momentum for the, that was for the red, and for the blue is 0. So 8 plus 0 is 8. Okay? Now, remember we're doing an inelastic collision. This is what we're talking about for this period to fiddle with. So an inelastic collision is where they stick together after they collide. Okay? This is very common when two objects collide. If you just take two objects like a car and a truck, they often get entangled when they collide, and they form one mass afterwards. So what's the mass of the combined system? Well, the red cart is 1 and the blue cart is 1 kilo. So the combined mass when they're stuck together is 2 kilograms. Now you read this number off our simulation. Our simulation. So you will run the simulation, and when you do it, you'll see 4 meters per second go on the top. Okay. Now don't forget, if it's moving this direction, it's a plus 4 meters per second, and if it goes this direction, it'll be a minus 4 meters per second. Okay. So it was a plus 4. We're now going to calculate the final momentum of the system, and the final momentum, sigma F, PF, is equal to the mass of the final mass, which is this one here, the mass of the combined, multiplied by the mass of the combined, multiplied by the velocity of the combined. So 2 times 4 is 8. And what you should be noticing is the initial momentum, which is 8 here, will equal the final momentum there being 8. Okay? Right, so what you're going to do is now work your way through this simulation. At the end of this simulation, you will answer a question about momentum before and after, and then you will now change the masses in the second part. So the second part of this one here, we are going to change the red mass. I should have done that in red actually, that'd be better. So the red mass here and the blue cart's mass here. So that, and you've got different velocities that you can set. Okay, and we're still having the velocity for the blue cart in our second experiment as 0. And finally, in the last run down here, we're now going to change both the mass, the velocity of both the blue and the red carts. Don't forget, if it has a negative number in front of it, like this one here, those ones there are moving to the left. If it has a positive number, it's moving to the right. Okay? And when you multiply a positive and a negative, you'll get a negative momentum. So a negative momentum is momentum to the left. Okay. Have a go at doing this simulation, and then once you have it done and you've answered the questions, you can then try the second simulation, which is the next style lesson, which is on elastic collisions and inelastic collisions.